So finally, I'll be very quickly show you the moment of inertia calculations for two-dimensional and three-dimensional objects having uniform mass density, for simplicity. So for example, solid disk and solid cylinder, etc. So let's get started with the simple one. So let's consider a ring, just a thin ring having radius r. So how would you calculate the moment of inertia about the center of mass using calculus? So that is very easy. So you just need to do, the moment of inertia definition is r squared dm. And your let's choose a small differential mass dm at and which will be at a distance equal to radius, and then you just need to do the integration of r squared dm to calculate the total moment of inertia about the center of mass here. But r is constant, so you just need to do the integration of the dm. But the integration of the small mass dm is the total mass. So the moment of inertia of the thin ring about its center of mass is simply mr square. So that's really quick one. So next, so the moment of inertia of a thin circular disk about its center of mass. So how do you calculate? So first you have to do this trick. So you can divide, you can consider dividing this, solid disk into a thin spherical shell, right? These thin spherical rings having a radius r and thickness dr, right? This ring that you consider has a radius r and thickness is dr, right? And you can assume that the disk is made up of such many rings, and you can just integrate from 0 to r to calculate the total moment of inertia. So since this is a solid disk, so it's a two-dimensional object, so you have to now you have to define a surface mass density, mass per unit area. And this thin spherical ring has differential area as 2 pi r, which is the circumference, times dr thickness. So that's going to calculate the differential area of this spherical rings that you have assumed, right? And the surface mass density, which we call sigma, is dm over da, is has to be equal to total mass over total area. Because why? Because it has, we are considering this as a uniform mass density. So then what you need for integration is dm. Dm is mass over total area times differential area. So this is mass over pi r square, and differential area is 2 pi r dr, and then dm came out to be 2 twice m over r square r dr. And then finally, by definition, the total moment of inertia is r squared dm, and you're integrating from 0 to r, because this is consider because uh, each shell, this thin ring, has a moment of inertia r squared dm, and you're integrating from 0 to the radius, circumference, and then you just do this integration, and it came out, you will end up with the moment of inertia of a thin circular disk as 1/2 mr square, right? Mass times radius, 1/2 mass times radius square. And this is about the center of, if you choose the axis of rotation at the center of mass, right? Next, now instead of circular disc, if you have a thin rectangular plate, something like that, square plate or rectangular plate having length L1 and width L2, and let's say we choose the axis of rotation along this longer side, or you could choose the axis of rotation along this side as well, no problem. But if you choose the axis of rotation here, so how do you find the axis of moment of inertia about this axis? So again, first let's you can first consider, first you have to do some consideration. So you can consider this rectangular lamina, rectangular plate, as made up of many thin strips, thin rods, right, like this, and which has a thickness of dx, and then that's why its density, its mass, linear mass density is, since it is uniform, total mass over total length, total area, has to be equal to the differential density. So the density of this small strip you choose. So dm over area. So this is the L2, which is the length, right? And times dx, that's the total area of this small strip. And then dm is m over L1 times dx. So whatever we did is to calculate dm, because for integration we need dm. So now, since to calculate the total moment of inertia, we have to integrate from this end to that end. And remember, we assume this rectangular plate made up of many these thin rods. So you have to do integration from 0 to L1, which is the total length, right? And we know this thin rod has about its center of mass, right? A moment of inertia about the center of mass of a thin rod is 1/12 ml square, but its mass here is differential mass dm, right? Because that's how we define. So then the total moment of inertia is integrating this quantity from 0 to L, and then you will end up with, so finally you will end up with this, something like that, 1/12 m L2 square. Okay, that's the moment of inertia of a thin rectangular plate. So similarly, you can calculate very similar concept, moment of inertia of a solid cylinder. So you then we can consider, right? The solid cylinder is made up of many thin cylindrical shells having radius r, small r, and thickness dr. So then cylinder is a volume. So then you'll have to calculate the volume mass density, mass per unit volume. So this thin cylindrical shell has a differential volume of LDA, length times the area of this shell. And area of the differential area of the shell is 2 pi r dr times L is the differential volume. Since this is a uniform mass density, so the density of the cylinder is total mass over total volume is also must be equal to differential mass density, dm over dv. And dm is mass over volume times dv, and dv, this dv is given by this right here. And you're ready to integrate now. Since the total moment of inertia about the z-axis, this is the axis of rotation about the center of mass, is now you just need to integrate from 0 to r of um, uh, you know thin cells from 0 to r, right? Because this cylinder is made up of many cylindrical cells, and cylindrical cells has a moment of inertia r square mr square, whose mass is dm. So you're integrating from 0 to r, and then after calculating you will see the moment of inertia of the solid cylinder about its center of mass is 1/2 mr square, which is exactly equal to the moment of inertia of a circular disk. So finally, now you also need to just play with that. Actually, this won't be, in the exam, something like this. The solid sphere and the hollow sphere, right? And finally, some extras. If you have a cone, thin triangular slab, what would be the, how do you calculate the moment of inertia? So you have to do some calculation. So if you are interested, actually, is on the sample problems.